All right. Thank you very much. And welcome to our talk, Humanoids Driving Go-kart. So this is pretty much what we did, actually. But before we start, let's introduce ourselves. So I'm Thomas Endres. I'm an innovation hacker. Innovation hacking is something that we started like 12 years ago at our company, TNG Technology Consulting. And what we are doing there is basically we are trying out new things. We are trying out the latest and greatest technology that is not in production today, but it might be in production maybe 5 years down the line or something like that. So our first fine tune of an LLM was with GPT-2 that was relatively unknown by the time, and it was on social media comments when we did the so-called shitposting AI. And nowadays, we want to do something else. But before we do that, let's introduce Daniel.
Hello, I'm a consultant at TNG. For my client, I work as a research scientist, and my job is to make robots more intelligent so that manufacturing processes become cheaper.
Yeah, and hi. Oh, that went too far. I'm David. I'm also working for the innovation hacking and as a consultant at TNG, and I'm doing cool things with robots.
And of course, we have with us our technology ambassador, that's G1PO. It's a Unitary G1 robot, and those of you who have seen some Star Wars might probably get the reference. All right. So with that, we start with a little bit of history because we want to show where we came from with robotics. So robotics is not a new field, of course, and people always wanted to have something, an object that moves like a human, that can maneuver dangerous environments or something like that, like a human. And in ancient Greece, they already came up with ideas of how that could look like. But actually, the first robots or something that you could call like that, they are currently in the Deutsches Museum in Munich, actually, and it looks something like that. So that's the praying monk. And this one comes with movable arms and movable feet, and it can also move around a little bit, and you can just start the mechanics, and it's a completely mechanical system. And with that, it looks like this monk is praying, and you can also can move around in various degrees of freedom. So it has various degrees of freedom, various movement abilities, and you can see the mechanics back in this set. But now let's go a few hundred years forward, and we end up with something that we've been also working with a few years back, and this is the so-called Now robot. So here you can see the Now robot, and it is a humanoid robot. It is half the size of the G1 robot, maybe a little less or something like that. And it already comes with a lot of degrees of freedom, so you can move the feet around, so it can actually walk around, it can move its arms, and at the same time, it can also move its head. And it feels like it looks a bit like a little child, so it triggers cuteness reflexes or something like that. But you could also do a lot of things with this robot. So you can also learn using this robot, and all the cool things that we'll be talking about today will also be possible with this Now robot. The one problem that this small robot had is the stability, of course, because this one is walking on pretty hefty legs. A human has legs that are not that broad or something like that. But these come with stability issues, and that's why first of all, the Asimo robot failed miserably. So you can see it here. So that was back in the year 2000, actually, and they tried to make him climb stairs, but it did not work out like that. And here is where more stable alternatives come in, and this is the Atlas robot from Boston Dynamics. You probably have seen this one. This is specifically built for stability, so it can stand on one leg, and you can just hit it with a wrecking ball or something like that, and it will still stand straight. And this is pretty cool. But at the same time, this one still comes with hydraulic motors, so it's not the same as you see with our G1. And that brings us to our G1.
Perfect. So now I can introduce G1. But before I start, who here programs in Python? Right. So this is great news because one of the key sort of advances of the last few years is that most robot manufacturers provide a Python SDK. So anyone can buy a consumer product like this. It's just 20 to 50,000 euros, and then you can begin programming in Python. So first big, let's say, new thing is you can program in Python. They also have a C++ SDK and ROS for those people who have a robotics background. And what you can do with that is you can move the motors on all of the limbs. And what you need for go-kart driving is to move the feet. Oh, for those on the right who can't see the robot, you're welcome to join us at the end and control the robot yourself. But let's start at the bottom and get to know G1. So we see he has feet, and those feet are needed to accelerate the go-kart and brake. And with the Python SDK, then we can do very simple foot movements, and we already have acceleration and braking. If we move up a bit, we have legs, and we saw, previously robots weren't very stable. Now they are very stable. So what I can do is I can shift the body weight onto the left leg, and you'll see he'll automatically raise his right leg. It's a subtle movement, but what it means is he can stabilize fairly well. It's loud, but he's pretty good at not falling over. So with feet and legs, we almost have everything to drive go-kart. We also need a hip to sit down. So the hip is smaller than the hip of a human. And we have an adult go-kart, so we had to come up with a solution. And our solution was the size of this is basically the size of a child. And there are tools we can use that are made for humans, in particular for children to drive go-karts, namely children's seats and pedal extensions. So we just went to Kart Plus and it got two children's seats and pedal extensions. And with that, he's already able to accelerate. So this is boring. And the next step is
to make it steer. First of all, we need to look at the chest of the robot. So in the chest of the robot is the battery. I'll just steal it from you. And since you on the left have the robot, you on the right get the battery. It's relatively small for a battery that can power that robot. I mean, consider the Asimov with like all of the diesel engines. And with that battery, we can move arms. So we made him do bicep curls. And essentially the idea here was, well, how much weight can those motors actually lift? Because they're sold to be very, very strong. And we wanted to steer a go-kart, which requires some strength. So what we did there was we took a bag, we filled it with 12, I think it was 12, bottles of water. And we then just made the robot lift it. And since we knew that was possible, we then looked at the hands. So if you look closely at the hands, you'll see that you have those metal plates here. Those metal plates are around like 2-3 millimeters thick. And now assume you have a steering wheel of a go-kart, which again gets the left side. I just want to show something here. And assume now I have too many things in my hand, but assume now I'm a robot and I have the other side of the steering wheel and I have all of the power to lift 12 bottles of water. And now I have like very, very fragile fingers and I lift like them up here and I hit the upper part. Then one of the fingers might break, which we didn't want to do because, I mean, Daniel already said it, the robot costs around like the price of a small car. So we chained it to the go-kart, essentially with the new steering wheel, which does the left side want it? That's a no. Okay. Then essentially we chained it to the steering wheel. So we just had like 2 chains and we placed the wrists of the robot inside of the chains. And then we could just like move the steering wheel left and right, which is cool because then we simply could interpolate the arm movements, and that allowed the G1PO to steer around the curve. So then we had maintenance problems. What this means is, I said the motors are quite strong, which is true, but we're also operating them at essentially they're close to their breaking point, which is not too healthy for an electronic motor. And essentially what happened was they zapped. And when we realized that, we had to buy a spare part, which was the wrist of the robot. I think the right one. And then we had to unscrew it. We had to cut the wires that are controlling the motor. We had to solder them back on. Then we had to rescrew everything. Then we had to recalibrate it. And in the end, like the recalibration was pretty easy. It was like a 15 minutes YouTube tutorial and pressing 3 buttons on an app. That was cool. The rest was kind of painful. And that essentially allowed us then to drive again. And then we had one problem. You have this steering wheel, and who of you had been driving karts? That's enough. Who of you had been bumping into the sideways? All right. Who of you had to press this reverse button? I mean, you have to, at least on the card we have. And if your hands are chained on a steering wheel, you cannot press this button. I mean, you can try. So we had to build our own button to make it drive backwards. And essentially, how this works is, I think we have the electronics here. You have like essentially a circuit here. If you press the button, you will just let the current float through, and then the cart will go forwards. And if you release the button, it will just go backwards, or the other way around. But I think you get my point. Since we couldn't make the robot press the button, we decided to use something that's called an FTDI controller. It's, in my opinion, a cooler version of Arduino. So it's essentially you can just program a few pins. Those pins are on a relay, and this relay is wired, as you can see on top, via a cable towards the circuit that would be closed or opened. And then we can just like plug that into the laptop that controls the robot. And that allowed us to actually put the cart into reverse mode or to forward mode. And that was actually the only thing we adjusted on the go-kart. Hello. And yeah, I think.
Well, that's it basically. So the humanoid robot is now able to drive, and obviously the first thing we do is to race it. We love Mario Kart, so what we attempted was we rented a Porsche and raced it. Okay, so hardware integration is finished. We've got a great video, and I think lots of people have seen videos online of humanoid robots doing cool things. So hopefully we've had a good look behind the curtain to see what's behind such a demo. But in general, humanoid robots have advanced a lot in the last 2 years. 5 years ago, it would cost as much as a house, maybe 200,000 or 300,000 euros. Now in 2025, it costs between 20 and 50,000, so as much as a car. And anyone with Python skills is able to program it. But typically, the use case of this is remote controlled. So someone, a human, is using their intelligence to control the robot. And for robots to really be useful, they need to be able to make decisions autonomously. And that's where we get to the last part, the head of the robot. So in the head, we've got a RGB camera. and a depth perception camera, a LiDAR, and with those, he's able to observe the world. And we use those to, for example, drive autonomously. So when he's sitting in a go-kart, it looks like this. On the left-hand side, you see the steering wheel in a go-kart, and at the top, it's like a QR code thing, which it can identify, and it knows that way what the front of the go-kart is. And on the right, we have depth perception. The different colors are how close and far away an object is. So one color will be for close, and the yellow and red colors are for objects far away. So we try to control the robot with VLMs, so vision language models that sort of can reason about vision input. And this robot has a GPU with which it could run VLMs, or at least small ones, but the small ones weren't good enough to, for example, decide how the robot needs to turn to stay on a line. So what we did, we placed a blue line on the floor and asked the VLM, should I turn left or right in order to follow the line? And the small models weren't good enough, and large models didn't run on the robots. We also tried connecting the robot to the internet and then deploying models on our GPU clusters, but that was just too slow. The latency was too high. So instead, we use classical algorithms, very simple 3 steps. First, we get rid of all of the pixels that aren't blue, and in that way, we identify the line, and we calculate what the angle of the line is. In the second step, well, you can use depth perception to identify the front of the go-kart, or you can use the Arduino code or the QR code that you see on the right picture. And then by comparing the front of the go-kart to the line, you can tell the robot whether to turn right or left. So if the line is to the right of the go-kart, it needs to turn more right, and if it's to the left, more left, and then that's regulated with a PID controller. So we've made robots a bit smarter to drive go-karts, but how do we make them in general intelligent?
Okay, so now we want to talk about how do we actually make the robot walk, because now it comes with a predefined walking method, but at the same time we also wanted to train our own, and our ultimate goal will at some point be to make the robot dance or something like that, which it cannot do by now. So one question that we ask ourselves, how can we make the robot learn? And in order to make the robot learn, of course, we have to capture some data. And we are pretty good at data capturing because we've done this with the Now robot already before. So that's our experience level. So we can really do that. So you can actually do something like that. So you basically do what the robot should do, and the robot will mimic your behavior. And if you don't want to it to look like that or that's silly, you can also do that in a more professional way. And this is how we did it then. So we have an Apple Vision Pro, which adds another 4,000 euros to your bill. And with that, you can then, first of all, see through the eyes of the robot. So you can just stream the image that comes from the sensors from the Intel RealSense camera that the robot has built in. And you can then just see through its eyes. And at the same time, you can measure where your hands are. And basically, you can then just adjust the different motors to the angles of your limbs. And with that, you can then control the robot. And you do that quite a lot. And then you can capture the data that you have. But if we don't want to capture all that data, if we don't really want to do this ourselves, we can also think about how could the robot learn by itself. And this is where reinforcement learning comes in. And reinforcement learning basically means that you just put the robot in an arbitrary environment, preferably standing up or something like that. And then you just give the robot a specific goal. So if the robot does not fulfill this goal, you will punish the robot. If the robot fulfills the goal, you will reward the robot. So you are somehow interpreting the behavior of the robot in its environment, and the robot will then try to avoid the situations where it gets punished, and it will look for situations where it is rewarded. And of course, this is not the robot doing it, but a neural network that, and the cost function is somewhat beneficial when it comes to something that it wants to do. And since we don't want to ruin the robot, because we're just putting it in some environment and then trying to basically let it do what it wants to do on its own, the first things will of course be something like this. So it will basically just fall down all the time. And that's why we put it into a simulation environment. So when we have the luxury of a simulation environment, we have the luxury of not losing 50,000 euros with each of these falls. And at the same time, we can also think about something like putting not one robot there, but a few hundred at the same time, so it will learn a little bit faster. And after some iterations, it will then somehow figure out, so it has no clue what it's doing at the beginning. And at some point, it will figure out what is beneficial and what is not. And it will then try to do the beneficial actions. So in this case, what we now ask the robot to do is, to not fall down. It fails miserably at the moment. And at the same time, to move forward. So the first things it will try to do is, if it falls forward, then it might also just jump, because then it moves forward a little bit. So these are the first tries that it does. But at some point it will realize, okay, this does not help, because it will make you fall anyways. So what you can then do, what it will then do, it will at some point realize that if I move something like that, that might be beneficial, and it brings me forward, and it will not immediately make me fall. So with that, the robot has now learned something. It will still fall from time to time, but this was like after 2 hours of training on an RTX 4090 or something like that. After a few hours of training, it will look rather like that. And this is where we are heading. So this is what we want to achieve with the robot. The simulation environment that we are using here is Isaac Gym. And there are predefined assets for the G1 robot that you can use, and with that you can train for certain policies. So you can also train for it to follow some navigation patterns, like follow whatever I give you with the Xbox controller or something like that. So this is an arbitrary way of learning things for this specific robot. And when you have done this, and when you have succeeded with that, you can then put that into the real world. So basically what you have to do, you have to execute the neural networks, the trained neural network on the robot itself. The robot comes with an NVIDIA Jetson, so it is powerful enough to at least do some inference on some decent sized neural networks, so that's fine. And then you also have to map everything that we have for the motors in the simulation environment onto your real robot. And with that, you can then do it on the real device. And here you can see what it looks like. So Daniel, in this case, is just holding the robot because we don't trust it. But in theory, it would not fall down, at least until the end. So when we just stop the robot, because it would bump into the other wall or something like that. So this has been working quite well, actually. And the thing is, however, we do not just want the robot to learn some specific behavior. We want the robot to learn some generalized behavior. We want to say something to it. We want to say, okay, grab me a cup of coffee or something like that. And then it should just go forward to the coffee machine, press a button, bring the coffee to me. And this is not possible with this simple approach to reinforcement learning, because you would just have to switch modes or something like that. We want to have something which is not there yet, but which might be there in the future. Something that looks like that. So this is actually Groot. It's a robot foundation model. This is Groot 1.6, which was released actually today. and the video is pretty impressive. So what you can, so none of this behavior that you see here was actually controlled or something like that. So you just said to the robot, yeah, bring that that card to the shelf and just fill the shelf with the contents of the card or something like that. And this is where the so-called vision language action models come in. So now we have robot foundation model, which basically means that you need as an input for a neural network, basically the state of the motors. And at the same time, you get some camera footage, of course, because it also needs to see in its environment in order to navigate it. And then you will also put in something that is very familiar with you probably because you've all used LLMs before. So you can also prompt the robot to do something. This will go through a vision language action model. So what the difference between a standard LLM and the vision language action model is first of all, it's a little bit smaller because it needs to be performed multiple times a second. So with that, it would not be possible to have something like a billion, several hundred billion parameter model on that robot or something like that, but it's rather something like a 3 billion parameter model. And first of all, it will run through a vision language model, which is basically you can put, it's a multimodal large language model. And this will then be used as high-level input for a second stage that will basically just do the movements themselves. So given some specific impulse it gets from the earlier stage vision language model, this will be used to then output something meaningful. And meaningful in this case means that you can output the movements, so the differences that the motors might need to take in order to fulfill the task at hand. Okay, that was a very rough walkthrough through a VLA. We have a more detailed talk about this, but this is not something we want to talk about today. All right, so Daniel, what did we do with the robot?
Yes, so I can conclude it's an exciting time to work with robots because they're fully integrated systems. They're Python SDKs, and all of the hardware is integrated, so you can do your typical data processing on their GPU, and you can use the computer vision algorithms that have been developed in the last few years. What do? We go to the German Museum and use it as an education platform. So these humanoid robots aren't replacing people in the manufacturing industry yet, but they can be used as a really nice way to teach children about robotics and AI. So in the first picture, we saw robots are very stable, which means we have no problem with just walking around the museum next to children that are even smaller than the robots. The second thing is we taught it to drive go-karts, and we do that in a German museum. We give children rides across the outside of the German Museum. In the third picture, you see it's very interactive. So there's also a loudspeaker and microphone built into this robot, which means that you can have normal conversations when you integrate text-to-speech and speech-to-text. In January, we're for the first time going inside the robots and giving tours for children. So we've bought a trailer and hooked it up to the back of the go-kart. And the idea is to drive around the German Museum while the kids in the trailer talk about the exhibitions with the humanoid robot. We've done lots of other cool things. So we tried to teach it to cycle, for example. That didn't work out so well because balancing is hard. Yeah. Would you like to conclude?
Yeah, and this brings us to what do we want to do next with these robots? Of course, we want to continue our journey with the Deutsche Museum and go on doing some extraordinary stuff with it. But at the same time, we want to move on to these robot foundation models. We want to really employ them with the G1, make them do something meaningful or something like that. But the robotic journey is not only about humanoid robots, so we are also using those for industrial robots. So we also have a UR5 robot from Universal Robotics trying to teach it to play chess, actually. which is pretty cool actually. And then we also do a lot of work with cobots. So-called leader-follower systems. So basically, we can do some laundry folding with that and try out things with the robotic foundation models as well. And with that, I think that's it for our talk.